so simple we don't need to focus on attention or ignoring, so we'll skip over it for now. And this prediction of saw, not dug, is passed forward. And again, for the purposes of simplicity, let's say there's no memory at the moment, so saw and dug get passed forward, and then the selection mechanism here has learned that when the most recent word is a name, then what comes next is either going to be the word saw or a period. So it blocks any other names from coming out. So the fact that there's a vote for not dug is blocked here, and the word saw is sent out as the prediction for the next time step. So we take a step forward in time now. The word saw is our most recent word and our most recent prediction. They get passed forward to all of these neural networks, and we get a new set of predictions. Because the word saw just occurred, we now predict that the words Doug, Jane, or Spot might come next. We'll pass over ignoring and attention to this example, and we'll take those predictions forward. Now, the other thing that happened is our previous set of possibilities, the word saw and not dug, that we were maintaining internally, get passed to a forgetting gate. Now, the forgetting gate says, hey, my last word that occurred with the word saw, based on my past experience, then I can forget about, I know that it occurred, I can forget that it happened, but I want to keep any predictions having to do with names. So it forgets saw, holds on to the vote for not dug, and now at this element by element addition, we have a positive vote for Doug, a negative vote for Doug, and so they cancel each other out. So now we just have votes for Jane and Spot. So those get passed forward. Our selection gate, it knows that the word saw just occurred, and based on experience, a name will happen next. And so it passes through these predictions for names, and for the next time step then, we get predictions of only Jane and Spot, not Doug. This avoids the Doug saw Doug period type of error and the other errors that we saw. What this shows is that long short-term memory can look back 2, 3, many time steps and use that information to make good predictions about what's going to happen next. Now, to compare to vanilla recurrent neural networks, they can actually look back several time steps as well, but not very many. LSTM can look back many time steps and has shown that successfully. This is really useful in some surprisingly practical applications. If I have text in one language and I want to translate it to text to another language, LSTMs work very well. Even though translation is not a word-to-word process, it's a phrase-to-phrase, or even in some cases a sentence-to-sentence process, LSTMs are able to represent those grammar structures that are specific to each language, and what it looks like is that they find a higher-level idea and translate it from one mode of expression to another, just using the bits and pieces that we just walked through. Another thing that they do well is translating speech to text. Speech is just some signals that vary in time. It takes them and uses that then to predict what text, what word is being spoken, and they can use the recent history of words to make a better guess for what's going to come next. LSTMs are a great fit for any information that's embedded in time. Audio, video. My favorite application of all, of course, is robotics. Robotics is nothing more than an agent taking in information from a set of sensors, and then based on that information, making a decision and carrying out an action. It's inherently sequential, and actions taken now can influence what is sensed and what should be done many time steps down the line. If you're curious what LSTMs look like in math, this is it. This is listed straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically can actually make a fairly straightforward picture and story. And if you'd like to dig into it more, I encourage you to go to the Wikipedia page. Also, there are a collection of really good tutorials and discussions, other ways of explaining LSTMs that you may find helpful as well. I'd also strongly encourage you to visit Andrej Karpathy's blog post showing examples of what LSTMs can do in text. And if you haven't seen it yet, take a look at the video on how neural networks work to get some more details on exactly how you go about implementing something like this in code. Thanks for tuning in. I wish you a lot of luck on your next project, building with recurrent neural networks. Neural networks are good for learning lots of different types of patterns. To give an example of how this would work, imagine you had a 4-pixel camera. So not 4 megapixels, but just 4 pixels. And it was only black and white. And you wanted to go around and take pictures of things and determine automatically then whether these pictures were of solid, all white or all dark image, a vertical line, or a diagonal line, or a horizontal line. This is tricky because you can't do this with simple rules about the brightness of the pixels. Both of these are horizontal lines, but if you tried to make a rule about which pixel was bright and which was dark, you wouldn't be able to do it. So to do this with the neural network, you start by taking all of your inputs, in this case our 4 pixels, you break them out into input neurons. And you assign a number to each of these depending on the brightness or darkness of the pixel. +1 is all the way white, -1 is all the way black, and then gray is 0, right in the middle. So these values, once you have them broken out and listed like this on the input neuron, it's also called the input vector, or array. It's just a list of numbers that represents your inputs right now. It's a useful notion to think about the receptive field of a neuron. All this means is what set of inputs makes the value of this neuron as high as it can possibly be. For input neurons, this is pretty easy. Each one is associated with just 1 pixel, and when that pixel is all the way white, the value of that input neuron is as high as it can go. So black and white checkered areas show pixels that an input neuron doesn't care about. If they're all the way white or all the way black, it still doesn't affect the value of that input neuron at all. Now, to build a neural network, we create a neuron. The first thing this does is it adds up all of the values of the input neurons. So in this case, if we add up all of those values, we get a 0.5. Now to complicate things just a little bit, each of the connections are weighted, meaning they're multiplied by a number. That number can be 1 or -1 or anything in between. So for instance, if something has a weight of -1, it's multiplied and you get the negative of it, and that's additive. If something has a weight of 0, then it's effectively ignored. So here's what those weighted connections might look like. You'll notice that after the values of the input neurons are weighted and added, the final value is completely different. Graphically, it's convenient to represent these weights as white links being positive weights, black links being negative weights, and the thickness of the line is roughly proportional to the magnitude of the weight. Then after you add the weighted input neurons, they get squashed. And I'll show you what that means. You have a sigmoid squashing function. Sigmoid just means S-shaped. And what this does is you put a value in, let's say 0.5, You run a vertical line up to your sigmoid, and then a horizontal line over from where it crosses, and then where that hits the y-axis, that's the output of your function. So in this case, slightly less than 0.5. It's pretty close. As your input number gets larger, your output number also gets larger, but more slowly. And eventually, no matter how big the number you put in, the answer is always less than 1. Similarly, when you go negative, the answer is always greater than -1. So this ensures that that neuron's value never gets outside of the range of +1 to -1, which is helpful for keeping the computations in the neural network bounded and stable. So after you sum the weighted values of neurons, squash the result, you get the output. In this case, 0.746. That is a neuron. So we can call this, we can collapse all that down. And this is a neuron that does a weighted sum to squash the result. And now instead of just one of those, assume you have a whole bunch. There are 4 shown here, but there could be 400 or 4 million. Now to keep our picture clear, we'll assume for now that the weights are either +1, white lines, -1, black lines, or 0, in which case they're missing entirely. But in actuality, all of these neurons that we created are each attached to all of the input neurons. And they all have some weight between -1 and +1. When we create this first layer of our neural network, the receptive fields get more complex. For instance here, each of those ends up combining 2 of our input neurons. And so the value, the receptive field, the pixel values that make that first layer neuron as large as it can possibly be, look now like pairs of pixels, either all white or a mixture of white and black, depending on the weight. So for instance, this neuron here is attached to this input pixel, which is upper left, and this input pixel, which is lower left, and both of those weights are positive. So it combines the 2 of those, and that's its receptive field. The receptive field of this one plus the receptive field of this one. However, if we look at this neuron, it combines this pixel, upper right, and this pixel, lower right. It has a weight of -1. Now, because we were careful of how we created that first layer, its values look a lot like input values. And we can turn right around and create another layer on top of it the exact same way, with the output of one layer being the input to the next layer. And we can repeat this 3 times, or 7 times, or 700 times for additional layers. Each time, the receptive fields get even more complex. So you can see here, using the same logic, now they cover all of the pixels, and more special arrangement of which are black and which are white. We can create another layer. Again, all of these neurons in one layer are connected to all of the neurons in the previous layer, but we're assuming here that most of those weights are 0 and not shown. It's not generally the case. So just to mix things up, we'll create a new layer, but as you notice, our squashing function isn't there anymore. We have something new called the rectified linear unit. This is another popular neuron type. So you do your weighted sum of all your inputs, and instead of squashing, you do rectified linear units. You rectify it. So if it is negative, you make the value 0. If it's positive, you keep the value. This is obviously very easy to compute, and it turns out to have very nice stability properties for neural networks as well in practice. So after we do this, because some of our weights are positive and some are negative, connecting to those rectified linear units, we get receptive fields and their opposites. You look at the patterns there. And then finally, when we've created as many layers with as many neurons as we want, we create an output layer. Here, we have 4 outputs that we're interested in. Is the image solid, vertical, diagonal, or horizontal? So to walk through an example here of how this could work, let's say we start with this input image shown on the left. Dark pixels on top, white on the bottom. As we propagate that to our input layer, this is what those values would look like. The top pixels, the bottom pixels. As we move that to our first layer, we can see the combination of a dark pixel and a light pixel summed together get us 0, gray. Whereas down here we have the combination of a dark pixel plus a light pixel with a negative weight. So that gives us a value of -1 there. Which makes sense because if we look at the receptive field here, upper left pixel white, lower left pixel black, it's the exact opposite of the input that we're getting. And so we would expect its value to be as low as possible, -1. As we move to the next layer, we see the same types of things, combining zeros to get zeros, combining a negative and a negative with a negative weight, which makes a positive, to get a 0. And here we have combining 2 negatives to get a negative. So again, you'll notice the receptive field of this is exactly the inverse of our input. So it makes sense that its weight would be negative, or its value would be negative. And we move to the next layer. All of these, of course, these zeros propagate forward. Here, this is has a negative value, and it has a positive weight. So it just moves straight forward. Because we have a rectified linear unit, negative values become 0. So now it is 0 again too. But this one gets rectified and becomes positive. Negative times negative is positive. And so when we finally get to the output, we can see they're all 0 except for this horizontal, which is positive. And that's the answer. Our neural network said this is an image of a horizontal line. Now, neural networks usually aren't that good. They're not that clean. So there's a notion of, with an input, what is truth? In this case, the truth is this has a 0 for all of these values, but a 1 for horizontal. It's not solid, it's not vertical, it's not diagonal. Yes, it is horizontal. An arbitrary neural network will give answers that are not exactly true. They might be off by a little or a lot. And then the error is the magnitude of the difference between the truth and the answer given. And you can add all these up to get the total error for the neural network. So the whole idea with learning and training is to adjust the weights to make the error as low as possible. So the way this is done is we put an image in, we calculate the error at the end, then we look for how to adjust those weights, higher or lower, to either make that error go up or down. And we, of course, adjust the weights in the way to make the error go down. Now, the problem with doing this is each time we go back and calculate the error, we have to multiply all of those weights by all of